Okay. Thank
The stage is yours.
Okay. Thanks, Angela. Good morning, everybody, and welcome to the 2020 edition of the ASTER workshop, Advances in Information Systems and Technologies for Emergency Management, Risk Assessment, Mitigation based on the resilience concepts. This is the first part of the workshop, which will be divided in two parts. Now I will show you briefly the program of this morning. And first of all, I would like to thank the other organizers, Marco Vona, Amedeo Flora, Chiara Iacovino, and Beniamino Morgante from University of Basilicata. My name is Maurizio Pollino. I'm a researcher at ENEA, the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. I will introduce the presentations of the first part of this workshop. That we will have in the first part 3 presentations from Amedeo Flora, Chiara Iacovino, and Alessandra Marra. And in the second part, which will follow this part, we will have 3 other presentations from Marco Vona, Sergio Cappucci, and Antonino D'Alessandro. So we will see different applications dealing with the topics of our workshops. Our workshop related to geomatics, earthquake engineering, risk assessment, critical infrastructure protection, and also to the resilience evaluation. And I would like to remember to the presenter that they have available 8 minutes for their presentation, plus 2 minutes for questions. The reason is that we are online, so it is important to reduce the length of the presentation in order to catch the attention of the participants. But of course, if you have any question for the presenter, you can use via the Jitsi platform. You can use the raise your hand icon in the lower left side of your layout. And if you are following this workshop via YouTube live streaming, you can use the chat to type your question, and then we will try to transfer your question to the presenter. And of course, if you are not speaking, I please you to mute your microphone. So we can start with the presentation, the first presentation of today. Just information. Is there? Good morning, Marco. Are you online? Good morning. And is there also Alessandra Marra?
Yes. Hello.
Okay. Okay. So all the authors which will present their works in the first part are now online. So Amedeo Flora, Chiara Iacovino, and Alessandra Marra for the first 3 presentations of this morning. And then the first one is from Amedeo Flora, from the School of Engineering of University of Basilicata, which will present a work co-authored with Chiara Iacovino, Donatello Cardone, and Marco Vona, Typological Inventory of Residential Reinforced Concrete Buildings for the City of Potenza. And in this work, the authors have investigated the built heritage of the city center of Potenza, in particular focusing on the residential reinforced concrete constructions. And they have identified several parameters by using an integrated approach involving census data, documentary analysis, on-site inspections, and GIS-based analysis. So I leave the floor to Amedeo for the presentation, and I remember your time availability is 8 minutes. So please, you can proceed. Thanks, Amedeo.
Okay, good morning, everyone. Can you hear me well?
Yes, perfectly.
Okay, so I will switch off my camera and I will share my screen. Do you see the presentation?
Yes, we can.
Yes.
Okay, good morning, everybody. My name is Amedeo Flora. I'm a researcher at the University of Basilicata. And the title of this presentation and the title of the related paper, as mentioned by Maurizio, is Typological Inventory of Residential Reinforced Concrete Buildings for the City of Potenza. First of all, let me say that the proposed study is just the first part of a larger research activity aimed at the evaluation of the seismic resilience of the examined area. And this study is funded by PON Research Project and is focused on the cultural heritage protection. The main goal of this part of the study is a preliminary investigation on the built heritage of the city center of Potenza, and also the identification of the main typological and structural features of the residential reinforced concrete RC constructions through an integrated approach based on census data, documentary analysis, site, and virtual inspection. The main product is then represented by a building typologies inventory composed by 36 elements, 36 typologies. The city of Potenza has been selected as case study. Potenza is the chief town of the Basilicata region in southern Italy, counting a population of about 70,000 people. And during its history, Potenza was hit by several strong earthquakes, and in particular, those of 1826, 1857, and 1980 caused severe damage, imposing a massive demolition and reconstruction activity in the historical city center. Moreover, from the urbanistic point of view, the demographic increment during 30s and 40s and the reconstruction plan of the early 90s produced the migration of the population to new urban areas located in the north of the city territory. All that considered, in the present study, two main sample areas, including most of the historical built heritage of the city, have been investigated. So the hilltop town, labeled as C1, and the residential public housing neighborhood, labeled as C2 in the figure. And those areas can be considered as homogeneous zone of compartments featuring specific historical, urbanistic, and constructive peculiarities. For what concerns the methodology for the inventory definition, we can say that the assembling approach is based on the combination of two different informative levels. The preliminary source is represented by census data provided by the Italian Institute of Statistics, ISTAT, but unfortunately these data are available only in aggregated form due to privacy policy. So secondary sources of information are needed to integrate the census data for the definition of the inventory. In the following slides, you can see some data obtained from ISTAT in the aggregated form, and in particular, first of all, the percentage distribution of residential buildings in terms of construction materials, the percentage distribution of residential buildings in terms of age of construction, and in terms of number of stories. So, focusing on the more relevant data, we can note that, first of all, in both compartments, the percentage of masonry buildings is prevalent, and as expected, this percentage is extremely high in the old town center, so C1, being equal to approximately the 80%. However, a significant percentage of RC buildings, approximately equal to 25%, is also observed. And this is probably due to some political decisions on the whole town planning taken between 1945 and 1970. In fact, in this period, many old masonry buildings in the historical center were demolished and replaced by new RC buildings, and similar interventions were carried out in the aftermath of the Irpina and Basilicata earthquake in 1980, and this led to a non-negligible percentage, around 10%, of RC buildings realized in the period 1981-1990. For what concerns the residential compartment, so C2, a percentage of RC buildings equal to 30% is observed, and this is quite unexpected since most of the buildings located in C2 have been realized during the period 1960-1990, that, as you know, is considered as the golden age for RC buildings. However, the previous consideration is completely overturned, reanalyzing the same data in terms of building volume. Moreover, considering that the seismic behavior is strongly affected by the structure height, important considerations can be derived analyzing the aggregated data with respect to the number of stories. And in particular, buildings featuring more than 3 stories are prevalent in both compartments, C1 and C2. But unfortunately, as mentioned before, based on the aggregated data, no specific information are available to effectively separate the percentage of low, medium, and high-rise buildings. Finally, we can note that the 10% of RC buildings have been realized after 1981 in both compartments, and this is very important considering that 1981 represents a milestone for the introduction of the first seismic regulations in Italy. So, based on the previous considerations, 2 main variables emerged as significant classification parameters, and in particular the number of stories and the age of construction. For the age of construction, 2 main groups have been identified: pre- and post-81 buildings. Obviously, a secondary informative level is needed to integrate the information gathered using the preliminary source. For the number of stories, different techniques have been used to rapidly collect georeferenced information on the number of stories of the building stocks located in the compartments, thus allowing a proper deaggregation of the mentioned data. For the age of construction, in order to identify the main characteristics of the 2 mentioned classes of buildings, pre- and post-1981, a comprehensive documental analysis and building surveys have been carried out. So, in this table summarizes the main peculiarities, the main characteristics of pre- and post-1981 buildings derived from the described investigation, and the combination of the main peculiarities for each class of buildings produces a different seismic behavior and, as a consequence, a different seismic vulnerability. So, preliminary typologies inventory in terms of seismic vulnerability can be defined, and in particular 3 different macro typologies can be considered, featuring low, medium, and high vulnerability, so L, M, and H. The preliminary inventory can be then further refined considering other specific building attributes that strongly affect the seismic behavior. So, besides the number of stories, other significant attributes are represented by irregularities in elevation and staircase typology. In particular, vertical irregularities are frequent for both pre- and post-1981 buildings and are mainly represented by an open ground story, so pilotis stories at the first floor. And on the other hand, 2 main staircase typologies have been considered: knee beams with cantilever steps and waist slab staircases. Then slight differences have been observed in terms of other attributes, such as roof type, horizontal floor, etc. So, such attributes have been neglected in the final inventory. The final building inventory, obtained adopting the described approach, is shown in this table, and as you can see, 36 classes have been finally identified, considering all the mentioned attributes. You can see number of stories, staircase typology, vertical irregularities, and all the peculiarities that are directly included in the micro typologies, L, H, and M. So, in conclusion, first of all, a simplified approach aimed at assembling of a building typology's inventory is presented and applied to the urban residential area of Potenza. A preliminary inventory for RC buildings has been defined based on heuristic criteria. Such preliminary inventory has been then refined considering specific building structural peculiarities affecting the seismic behavior. And it is important to note that, as mentioned in the first slide, this study represents just a primary step of a comprehensive research activity for the evaluation of the seismic resilience of the investigated area, and a complementary study regarding masonry buildings located in the same compartments has been carried out in parallel by the same authors of this paper and will be presented just after this presentation by my colleague Chiara Iacovino. So, thank you for your attention. If you have questions.
Okay, thank you very much, Amedeo, for your presentation. Very interesting. And of course, any questions? No questions, neither from YouTube, I see. Okay, I just have a question, which is also a curiosity. Amedeo, you say that this is a first part of a larger study, and you have described, of course, the methodology and the results obtained in this first part. But I'm curious to know which will be the next steps of this study, on which aspects and elements you will be focused in the future developments.
Okay. This is a very good question. Thank you for asking, Maurizio. And yes, this is, as I mentioned many times in the presentation, this is just the first part of a comprehensive research activity aimed at the evaluation of the seismic resilience of the examined area. So after the definition of the typological inventory, we are going first of all to define some numerical nonlinear models describing the seismic behavior of each typology, and actually this is what we are doing now. So this step is ongoing at the moment, and then we are going to carry out a large number of nonlinear analysis aimed first of all at the evaluation of the seismic vulnerability of each typology in terms of fragility curves. And then we are going to perform, using the results of the nonlinear analysis, a damage and loss assessment aimed at the definition of a single parameter defining the seismic quality of the building typologies, of the built heritage. So the seismic quality associated to the seismic resilience. Then in the last part, we hope to do another thing and to re-evaluate everything. So the seismic resilience of the examined area, considering the implementation of some retrofit interventions in order to compare the seismic resilience nowadays, so in the state of the art, and the seismic resilience after this potential retrofit intervention, and to define the improvement of seismic resilience of the examined area. So this is the complete picture of the research.
Okay, thank you for your clarification, which provided us the overall picture of your research that I guess will proceed for the next. How many years are?
The PON research activity is 3 years. So okay. I think that at the end of the second year we will be able to perform all the nonlinear analysis. Then we have to apply this probabilistic approach for the definition of this parameter that in practice is the expected annual loss, and then we have time to reevaluate everything for the last part, and so the emanation of the results.
Okay, thank you very much. Thank you again. Before to start with the next presentation, I think that we can spend 10 minutes for each presentation, because we have only three presentations in the first part and other 3 in the second part. also Amedeo used the 10 minutes, and I think that in this situation is the perfect timing, considering the number of works presented. So please consider 10 minutes for your presentation. And then I would like to invite you to type your name in your avatar by clicking on the 3 vertical dots in the lower right part of your layout, so that when you possibly make a question, we can see your name. And finally, another suggestion. My proposal is to make all the 6 presentations in continuity, so that after the presentation by Alessandra Marra, we will promptly continue with the other presentation from Marco Bona, Sergio Cappucci, and Antonino D'Alessandro. If you agree, I suggest to make all the 6 presentations in a row. Okay. So I will invite Chiara Iacovino to prepare their presentation. Chiara Iacovino from School of Engineering of University of Basilicata, and along with Amedeo Flora, Donatello Cardona, and Marco Bona, Chiara will present work entitled Defining a Monthly Building Inventory for the City of Potenza. As Amedeo said before, this paper is a work carried out in parallel with the previous one, but in this case, this work was focused on the existing masonry buildings of the historic center of Potenza. And also in this case, the authors have exploited several integrated techniques and approach, such as documentary analysis, census data, on-site investigation, and GIS-based analysis in order to perform their assessment. So I leave the floor to Chiara for her presentation. Please, Chiara.
Okay, thank you, Maurizio. Can you hear me?
Yes, perfectly.
Okay. Can you see my screen?
Yes,
okay.
Yes, we can.
Thank you. Hello, everybody. I am Chiara Iacovino, a researcher from the University of Basilicata. As my colleague Amedeo Flora said before, these works are part of a research study carried out within a PON project, and I will present this work that concerns the masonry buildings located in the investigated area. The seismic vulnerability assessment of masonry built heritage is an important issue in Italy due to the high seismic hazard of the territory and the huge amount of masonry buildings located in the exposed areas. One of the main challenges of a large-scale seismic vulnerability assessment is the need for collection of data about a large number of buildings, but access to such large amount of data is usually difficult, and cities, including historical heritage, usually have incomplete construction databases. So being able to classify the built heritage in a limited number of specific structural typologies with similar characteristics would simplify the vulnerability assessment. The aim of this work is the definition of a typological and structural classification of existing masonry buildings of the historic center of Potenza. As I said before, these works are carried out on the city of Potenza, located in the Basilicata region in the south of Italy. The methodology is the same as that presented before by my colleague. So to define a specific building typologies inventory, the combination of two different informative levels has been used. The official national census database is provided by the Italian Institute of Statistics, were used as the primary source for the classification of the building stock. But due to the aggregated form, these data have been integrated through other sources of information represented by extensive documental and virtual analysis and specific building surveys. This figure shows the census areas of Potenza, while the table reports the values of resident population and residential buildings in each census area. As we have seen before, in these works, two main sample areas have been chosen. The Old Town Center that is included in census area number 1 and the residential public housing neighborhood that falls in census area number 3. In these works, only the private residential building stock has been considered. This figure shows the selected census tract of the Old Town Center in yellow and of the residential compartment in blue. The tables report the aggregated data of the buildings located in the two compartments. We can see that the percentage of masonry buildings is high in both compartments, being equal to approximately 80% in the Old Town Center, but is also high in the residential compartment, where most of the buildings were built with a load-bearing masonry structure during the period 1940-1960. Buildings featuring more than 4 stories are prevalent in both compartments, but due to the aggregated form of this data, no information is available to separate the percentage related to masonry buildings from the percentage related to reinforced concrete buildings. And finally, we can see that in the historic center of Potenza, most of the buildings were built before 1919. In addition to census data, comprehensive documental analysis has been carried out. In particular, a large database provided by the local organization of social housing has been analyzed. Then building by building surveys have been performed, and finally other information has been obtained interviewing local technicians with deep knowledge of the construction characteristics. The most significant parameters, in addition to the number of stories and the period of construction, for example, the type of vertical and horizontal structure, the type of roof, the presence of vault, the presence of mixed structures, and so on, have been considered. This table summarizes the main characteristics of the masonry constructions named Moore derived by the investigation. The Moore 1 typology concerns the first buildings built outside the historic center during the 1920s. The buildings are made of regular masonry with floors with hollow bricks and steel beams, and no connections are present. So the seismic behavior of this typology of construction is usually ruled by the out-of-plane mechanism. The features of the Moore 2 typology are external walls made of cut stone with good bonding and a vault floor with bricks and steel beams. Over the years, some of these buildings have been subjected to localized seismic intervention, consisting mainly of widespread connections. The third typology groups constructions made by solid brick masonry with a rigid slab and connections between vertical walls and horizontal elements. This type of buildings is usually characterized by a box-like seismic behavior. In the 1950s, the urban landscape was remodeled with the presence of reinforced concrete buildings. In fact, if we see the Moore 4 typology, it's characterized by external masonry walls with internal reinforced concrete beam column systems with rigid floor. And finally, the last typology characterizes the reconstructed buildings of the historic center of Potenza after the Irpinia and Basilicata earthquake. So the ancient masonry was replaced by regular masonry made of solid brick stones, and the deformable timber floors were replaced by rigid slab. Furthermore, widespread seismic improvement interventions were performed. Well, the management of the collected data and the development of graphical outputs are important activities during and after the surveys. GIS applications are among the most suitable tools to generate databases as well as to store, analyze, and manage a large amount of building information. This figure shows a GIS mapping of the different structural typologies. The preliminary inventory, composed by 5 macro typologies, has been further refined considering other building characteristics. With regard to the number of stories, the analyzed masonry structures can be grouped into 3 classes: low-rise, medium-rise, and high-rise buildings. With the reference to the shaping plan, other 2 classes have been considering, and finally, other 2 classes have been identified taking into account the presence or not of the slab wall connection. So, starting from 5 macro typologies and then considering 3 classes for the number of stories, 2 classes with the reference to the shaping plan, and other 2 classes with the reference to the slab connection. Finally, we have identified 60 typologies. To conclude, in this work, a simplified approach aimed at the design a masonry building inventory is presented and applied for the urban residential area of Potenza. A preliminary inventory has been defined and then has been further refined considering other specific building structural characteristics, arriving to 60 typologies. It's worth noting that the other characteristics, such as the structural element dimensions, the building position in a block aggregate, and the percentage and arrangement of openings in walls, will be taken into account at a later stage of the research project, in particular during the numerical modeling of the selected buildings. Thank you for your kind attention.
Okay, thank you, Chiara, for your presentation. Very interesting. And of course, I am inviting the other participants to make some questions if they have something to ask. No questions, neither from YouTube. Chiara, you can stop your sharing. Yes, by clicking the icon. Okay, perfect. Thanks. Okay, so I have a question about the buildings typologies considered. In this study, you focused on residential buildings. Yes. Is it correct? Which are the reasons of this choice to select this typology instead of other particular typologies? I mean, historical and cultural heritage buildings and so on. How do you can explain the reason of this choice?
Yes, thank you, Maurizio. At the beginning of the project, we thought to consider or not also the historical heritage included in the investigated compartment. However, historical and monumental buildings consisting mainly of masonry material are complex systems that require specific and detailed knowledge and information regarding their response under seismic excitation, as well as appropriate modeling. Moreover, these structures, such as churches, monasteries, and so on, are subject to protection, and there are specific codes. For example, the Italian guidelines of cultural heritage and the landscape. Also, another issue is the access to the data regarding to these structures. For example, historical documents or construction databases. It can be more difficult due to the lack of information and documents and due to the permissions to access to this data. So for this reason and this time, we decided to consider only the private residential buildings. Probably at a later stage of the project, we could also include some historical buildings with specific studies.
Okay, thank you. It is clear. In fact, the modeling and data retrieving concerning historical buildings is a very hard task to be accomplished for the reason that you have described. So I understand the reason. In fact, sometimes there are projects which are focused only on historical buildings, yes, because they are very specific and particular from many points of view, from the structural point of view, from the historical point of view, and the last but not least, from the considering the difficulty to retrieve documents, to perform in situ analysis, and because you have to consider also the constraints linked to the special protections concerning these sites, the legislations, the authorities, and so on and so forth. I understand. Thank you very much again, Chiara. Okay, so I'm inviting Alessandra Marra to prepare her presentation. Alessandra Marra will present a work co-authored along with Roberto Gerundo, Antonio Nesticò, and Maria Carotenuto, all from the Department of Civil Engineering of the University of Salerno. A model to mitigate the peripheralization risk at urban scale. Sorry. This work aims to provide a model for the mitigation of this phenomenon regarding the peripheral areas at risk in urban context. And so for this reason, the authors described a model in which a set of mitigation indicators are assessed and evaluated, also using, for instance, an analytical hierarchy process, AHP. And this activity will be described in the next presentation, so I leave the floor to Alessandra Marra, please.
I'm sorry.
Alessandra,
at the moment I have problem with my presentation. When I share my screen, I have some difficulties. I try again.
Try again to share your screen. Okay, yes. And then after you are sharing the screen, you have to click to the PowerPoint icon. Okay, okay, go on your instrument bar. Okay, perfect. Okay. And then you can start the presentation mode. Yes, now we can see the presentation, and then switch in presentation mode.
Yes.
Perfect. Okay, okay. It's all okay.
I am Alessandra Marra from University of Salerno, where I am a PhD student, and I work with the research group of urban planning techniques directed by Professor Roberto Gerundo, and this work is the result of a collaboration with Professor Antonio Nestico from Project Evaluation Laboratory. The expansion of cities and of multiple forms of poverty on a global level has changed the geography of degradation. In Europe and in Italy, degraded urban areas are often associated with peripheries, born starting to the age of historic city centers. But nowadays it is appropriate to talk about peripheralization rather than peripheries. As some scholars really observed also in other disciplines, such as economic geography, social sciences, and so on. Peripheralization is intended as a dynamic process that produces degradation in spatial peripheries, with reference to peri-urban areas where risk is mainly connected to sprawl and land consumption. But this process can also affect typical central areas with reference to the multidimensional concept of urban poverty or to the European one of deprivation. All these processes, of course, are associated with unsustainability, reducing land consumption and urban poverty through the regeneration of deprived areas are key issues to the new urban agenda and to European Union. In fact, over the years, the European Commission has financed several actions to reduce degradation and with, for example, urban regeneration projects. In Italy, scientific criteria are generally not used for the identification of degraded areas subject to intervention, but their recognition is usually delegated to the municipal authorities, on the occasion of call for funding. Interventions are mainly driven by economic convenience in real estate transformations. In contrast to this, some scholars propose multi-criteria evaluations of project proposals in order to maximize public benefits. Among the different techniques, the use of the analytical reactive process is frequent. In fact, it allows to consider a greater number of criteria, an important feature in the evaluation of complex programs, such as regeneration programs. However, in the light of the new urban and socioeconomic geography, regeneration interventions must be directed primarily to the most vulnerable areas. So, decision about the most effective project proposal should be informed of persisting vulnerability levels, and this is possible when the planning and the localization of interventions takes into account the multi-criteria evaluation of the best design alternative, and this is the idea, our idea, and the novelty of the work. So the objective of this work is to characterize a model for the mitigation of peripheralization risk at urban scale, so as to provide a decision support system for the choice of the best design alternative in order to maximize risk mitigation. This contribution is part of a wider research project. According to our approach, priority areas are those in which the greatest risk of peripheralization occurs. We already defined peripheralization risk as the product of aggregated vulnerability and exposure. Aggregated vulnerability is given by the combination of social, building, and urban vulnerability, while elements at risk are population, building, and urban fabric, with respect to these dimensions. A set of vulnerability indicators has already been designed to map peripheralization risk. The greatest risk of peripheralization occurs where high levels of aggregated vulnerability occurs, given by the combination of social building and urban one. Following that work, the method here proposed identifies a set of mitigation indicators with specific reference to vulnerability indicators used for the localization of priority areas. Mitigation indicators here proposed allow to estimate the effects of project proposals on social building and urban domains, with the aim of reducing vulnerability and therefore risk. The first phase is the definition of mitigation indicators, then the procedure is articulated in the all phases of the analytical hierarchy process with a little variation, as we will see. With reference to the social domain, mitigation indicators measure new employees, graduates in secondary school, and the ability of the city physical functional structure to attract young families. With regard to the building domain, they measure interventions to improve the state of building housing stock. While for the urban domain, indicators estimate actions aimed at increasing supply of services and permeable green spaces, recovery of abandoned or degraded areas, as well as reducing the fragmentation of the urban fabric. The proposed dominance hierarchy consists of 3 levels. At the highest level, there is the objective, of course. At the second level, there are the criteria, which correspond to vulnerability domains. At the third level, there are the sub-criteria to which mitigation indicators correspond. All 10 sub-criteria are measurable for each of the K-design alternatives, among which the decision maker is called to choose. For each design alternative, the values of mitigation indicators constitute the lines of the decision matrix, while the columns relate to the values of the specific sub-criteria. We proceed to the pairwise comparison of project proposals with respect to each criterion. I'm sorry. Then to the pairwise comparison of sub-criteria for each domain, and then to the pairwise comparison of criteria. The pairwise comparison was carried out with reference to Satie semantic scale useful for the attribution of dominance coefficients. In the pairwise comparison of criteria in particular, analysis in different scenarios are possible. For example, in the first scenario, all criteria have the same importance, while a very relevant scenario that is possible to consider is that where the weight of the criteria depends on the vulnerability levels obtained from the peripheralization risk analysis already carried out in the research project. For each domain, vulnerability maps return different classes, low, medium, high, and very high, as you can see. The linguistic values low, medium, high, and very high can be converted into proportional scalars. In particular, low value will correspond to the scalar 1, while the very high value to the 4. The scale in figure allows to divide the 4 ranges, 1, 2, 3, and 4, into the 5 typical Satie value ranges. In this way, we can define dominance coefficients. And at this point, we are able to evaluate the priority of one project proposal over the other. In particular, we refer to the principle of hierarchical composition. We have recently applied the model to a case study, so I'll show very quickly the results, even if it isn't in the paper, because it's a very recent application. The study area was one of priority areas obtained by peripheralization risk analysis. It is in Marcianise municipality in Campania region, Italy. And these are vulnerability levels obtained in social building and urban domain. So in this case, decision makers have choice among three different project proposals which involve different interventions. I show very quickly the results. In the zero scenario, all the criteria have the same importance, while in the other one, weights of criteria depend from vulnerability levels. And in this case, we had a high social vulnerability and urban vulnerability, while a medium building vulnerability. So on the right, we can see the priorities of project proposals. Very quickly, the first proposal pays particular attention to the desealing of imperviousness areas. The second one gives emphasis to social animation, and it is more attractive to young families thanks to the creation of jobs and greater reception in schools. The third proposal emphasizes the increase in facilities and services. So the priority one is the second, as we can see. The methodology proposes a decision support tool to evaluate the effectiveness of urban regeneration interventions in terms of peripheralization risk mitigation. I want to underline that the proposed methodology requires the previous identification of urban areas most at risk, where regeneration interventions should be prioritized. And given that a high risk level depends on a significant aggregate vulnerability, the method for estimating that vulnerability is crucial, of course. And this is especially true because in the scientific community there is no agreement on what the most appropriate set of vulnerability indicators and how to combine them. So in the research project, in the broader research project to which the work belongs, a method of combining indicators based on the fuzzy logic was proposed, allowing to manage the uncertainty related to their aggregation. And following this work, we have defined the method here proposed. Future research developments may concern integration of the environmental domain and the implementation of related vulnerability and mitigation indicators. So, for example, air pollutants, urban waste, and fuel poverty can contribute to develop peripheral condition of urban areas. So, it will be certain of interest to analyze how results vary, considering also these aspects. Thank you for your kind attention.
Thank you, Alessandra, for your presentation. Very interesting also for you. I would ask to the other participants if they have any questions. Okay, from my side, just a question about the comparison criteria and the judgments provided according to the SATI approach. How many experts were considered in in this study, and which was their specific expertise to provide the judgments.
Okay, we performed the evaluation in synergy with the project evaluation laboratory, but we defined the so-called first scenario that we have seen depending on pre-existing vulnerability levels in order to reduce the subjectivity of choices made with respect to study scale. So the novelty of the work is the evaluation, the relation of the planning and localization of interventions in the most vulnerable areas with the evaluation of the best project proposal in order to maximize risk reduction, properly considering pre-existing vulnerability levels.
Okay, thank you, it's clear. Okay, thank you again, Alessandra, for your presentation. It's 10 o'clock, so we are in the second, we are fully in the second part of our workshop. So I just remember you that in this second part, we will have 3 presentations from Marco Bona, Sergio Cappucci, and Antonino D'Alessandro. And about the last presentation, I would ask if Antonino, if he's present online, Antonino, or anyone from INGV. No. So currently we have Marco and Sergio online for the presentation. So we will wait Antonino for the last presentation. So the next presentation is from Marco Bona. Marco, can I introduce you if you agree? It's a pleasure for me to introduce your presentation, of course. Marco will present the work changing from the emergency plan to the resilience plan, a novel approach to cyber protection and urban planning. And in this study will be presented the concept of resilience change in urban planning and emergency management. And for this reason, a specific case study was considered, and the improvement of the resilience was investigated in order to evaluate how it is possible to assess effectively the recovery and resilience and emergency strategies. So I leave the floor to Marco for his presentation, and you are welcome.
Okay, you can see my presentation.
Yes, we can see your presentation, but your mic level is low.
Okay. So, in this presentation, I speak about changing from the emergency plan to resilience plan. This is a novel approach to cyber protection and urban planning. So, currently, seismic risk mitigation is one of the main priorities at the global level. In fact, the consequences of the seismic events are often dramatic and not reversible. Then, you need tools, methods, and strategies in order to seismic risk mitigation and planning, urban planning, But for me, these strategies and the new methodology tools should be based on resident sponsor. So in this slide you can see the classic form of residence, but really from the recent approach, in Italy and in other European seismic prone countries, the residence is low or not existent. For example, in Latvia, in this slide you can see the repair and retrofit class for only slide damage in this slide for residential building. And you can see this trend of curve or curve of retrofit casting, and you can see that this is a real residence and community development. Then this is a new model for residence of community based on the real data, and then in the other side we have defined a new concept of seismic residence of community based on a new residence index, and in this way we can define the real residence of community and measure the residence of community based on this simply index. And we can measure the impact.
Professor Vona, sorry. Can
Yes.
I ask you to bring the microphone closer? Because it's very difficult to grasp the sentences.
Yes.
Sorry for the interruption.
Yes, I don't know. This is the best way for my book. You tell me. So, in this slide, you can see the effect of mitigation strategy, and the resilience can measure based on this resilience index. So, we need a strong modification of currently civil protection strategies, and based on some example in other parts of the world, for example, Los Angeles and San Francisco City. Then, really, in Italy and in other European earthquake-prone countries, the resilience is strongly related to their social, economic condition, structural and structural condition, and in particular, the presence of a stronger building and the factor needed to protect of and preserve the cultural heritage. So, in this slide, we can see the first application of this new trend for civil protection based on the classic residence concept based on reduction of seismic damage and losses, recovery time, and reduction of the downtime, so interruption of activity in order to protect the economic activities. This is the general framework of the study, based on the classic step in order to define the seismic scenarios for building stock. And the study is based on a simple case study, and the case study is a little town, Miglionico in Matera. This is a little town in south of Italy. So in this slide you can see the location of the case study in southeast of Italy, and this is the image of a little town, and we have we study this town based on the classic procedure to define seismic scenarios based on inventory of building, seismic vulnerability classes, assessment based on classic approach based on European microseismic scale. Then we consider the selection scenario with and representation of damage scenario based on damage probability methods. So in the slide you can see the survey of building in this case study and the subdivision in 4 different zones for historical center based on structural type, material and age of building. In the slide you can see the statistical distribution of vulnerability classes, and we have defined the classic step to resident study based on recovery time, and this is in this case the recovery time is based on the available data from Latvia and the subsegment reconstruction process. Then, based on the concept of resilience, different mitigation strategies are defined and investigated in this study. For each strategy, we have defined 1 or 2 steps or shift for vulnerability classes, or in the last strategy, the total rate of buildings. Then in this slide you can see the resilience trend for historical center and a new zone without any strategies. And in this slide you can see the effect of different strategies for historical center only. In this slide you can see on the left the first strategies based on 1 shift of vulnerability class, and on the right you can see the effect of the last strategies based on the total weight of the building. Then in this slide finally you can see the difference of the resilience index in the case study based on the different strategies of mitigation based on different recovery time and time point. So, conclusion, the concept of resilience and their quantification is used to define the urban regulation and effect. Improving the procedure is only possible defining an effect resilience based on the decision process in seismic risk prediction. This approach plays a key role for mitigation strategies and consequent structural design techniques. The choice should give several constant indications for design, construction of individual building or a retrofit of existing building. And then the key of the study is the replacement of emergency plan with resilience plans. Thank you for your attention.
And thank you, Marco, for your presentation. Very interesting. And any questions? Well, I just have a question which is also a wider consideration about this important issue which is related to the resilience and to the emergency. From the technical and scientific point of view, it is clear that the resilience plan is fundamental and is an effective tool to deal with the emergency. But which is your feeling about the institutional point of view? How the authorities are aware of such aspects for which we can shift from an emergency and post-event management of occurred events, and we will change our mind and start to improve our resilience plan in order to be more prepared for the calamitous events. In other words, the preparedness is already in the culture of our institution or not?
Yes, I think that this is a globally change of point of view. Then, emergency plans is a management of emergency. The resilience plan is a different point of view, and this is a new balance tools for any activities. But I think that is the core of the proposal is the real interest of uh, institution, administration, decision maker, and so on. And this is as one difficult step in order to find the real results.
Okay, thank you very much, Marco. Okay, Marco, if you agree, I will proceed with the introduction of the other works, or you will.
No, you can continue.
Because the second part is on charge to you. If you would like to introduce the other works, please, you are welcome. No problem from my side.
For your side.
Okay, thank you very much. The next presentation is from Sergio Capucci from ENEA, the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. In this work, co-authored along with Giacomo Buffarini, Ludovica Giordano, Salomon Aile Michael, Guido Martini, and Maurizio Vollino. Local geology and seismic induced damages, the case of Amatrice in central Italy. In this presentation, Sergio will show the preliminary results of the spatial correlation between the distribution of building damages generated after the earthquake event on 24th August 2017 in the central Italy, and the results of the seismic microzonation of the town of Amatrice. So I leave the floor to Sergio for his presentation. Please, Sergio, you can present your work. Sergio, you can switch on PowerPoint, okay? You can switch in presentation mode, okay. We cannot hear you. Yes, click on. Okay, click on. No, you should click directly on the icon. Yes. Switch off the drop menu. Click on the. No. Sergio, click on anyway in the GC layout. Anywhere in this, click outside of this, okay. Move the...
Maybe you can try refreshing your web page.
Okay, can you hear me now?
Okay,
now?
Okay.
Yes.
Yeah, sorry, I don't know what happened to the microphone. So you can see the PowerPoint and you can hear my voice, yeah? Hello?
Actually, we can't see your PowerPoint.
No?
No.
Okay. So let's see if...
Sergio, you have to share again your screen, I guess.
Let's try.
Okay. Okay.
So can you see the slide now?
Yes,
Yes.
I can.
Okay. Sorry, I don't know what happened. I apologize for that. So this is a presentation on the local geology and the seismic induced damages of the Amatrice downtown in central Italy. As you can see on this image, this is a shake map of the earthquakes that occurred on 24 August 2006. And on the right, you can see the different damage degree that has been mapped by the Copernicus EMS, the Emergency Management System. And on the bottom, you can also find some information about the schematic geological section across the central Apennine and the morphological profile, geological profile of the Amatrice Ridge that is just in front of the Tronto River Valley and is characterized by an underground subsoil of calcarenite and hard rock with an overtop by a quaternary layer. There is a landslide on the northeast sector, and Amatrice is just on top of this ridge. That is not the optimal condition for the earthquake amplification. So what happened immediately after the main shock is that the Italian National Civil Protection was in charge of the emergency and post-emergency activities, and Enea participated on many of these activities, but particularly on the working group for the determination of rubble volumes, the seismic microzonation activities in central Italy, the macroseismic survey, and the survey of co-seismic earthquake ruptures, the NRGEO. This is not our first publication. We started on 2007 with a short paper on lecture notes in computer science, and with this first paper, we basically investigated an expeditious approach to estimate the rubble hits volumes. With the second publication, we try to address the possibility to characterize the composition, the nature of these rubble hits, and through a multi-platform remotely sensed data. And we have been also able to detect the possibility and the presence of asbestos within the rubble hits. With this publication, we have another objective. We wanted to investigate the possibility to spatially correlate the building damage level distribution with the amplification factors mapped. So the data set is listed in this slide. We have used a digital terrain and surface model, orthophotos, the grading maps of Copernicus Emergency Management Service, digital cartography, and the seismic microzonation that was concluded last year, and you can find all the data set on this web page that is indicated at the bottom. The flow diagram of the procedure that we have implemented is illustrated in this slide. So we have used the information from Copernicus and LIDAR to determine the building damage degree and the rubble hits estimation. And through the use of digital cartography and the seismic microzonation, we have tried to correlate in terms of visual observation and statistical analysis the relation between the building damage and the different homogeneous zones. So this is a typical results that you can obtain with this approach. On the left, you can see the overlapping between the microzonation maps with an amplification factors between 0.1 and 0.5, and the different height of the building. With the brown color, you can see the highest building between 9 and 12 meters, and with the green color, you can see the few lower building up to 3 meters of height. On the right, you can see the same map, but overlapped by the different damage degree of the buildings. You can see with the red color, the completely destroyed buildings are located in within the area with the maximum amplification, and the green color are representing the not affected building. So through this data, it's possible to do some statistical analysis. This is a very simple table and bar diagram that basically demonstrate and compare the different damage degree for the number of buildings and the extension of the different areas characterized by different degree of amplification. So what you can see with the bar diagram is that with an increasing amplification factors, you have a general decrease of not affected buildings and a general increase of completely destroyed buildings. So the conclusion is that ground motion amplification due to local geological conditions are well-known effects, and quantitative analysis of such ground motion characteristics is fundamental for both damage evaluation as well as future urban planning and reconstruction. And the methodology of the present study allows to investigate the role of seismic ground motion amplification on the observed building damage. And this information can be summarized in seismic microzonation maps, where each microzone area is associated to an amplification factor. And the capability of GIS application are very important, as they can be the driver for both efficient intervention in order to reduce the building vulnerability of existing constructions, as well as new economic development models during the reconstruction phase. So those are the main issue that we have to present today with this short publication that we have already submitted. I think it's switch off. Okay. Hello? Yeah.
Okay, Sergio.
I finish.
Yeah, you can click su interrompi condivisione.
Yes.
Okay.
Here we are.
Thank you, Sergio, for your presentation. And any question? Of course, I am one of the co-authors of this work, so it is not so classy to to make a question. So I leave the floor to the other participants. Please go ahead.
Yes, I have one question. Have you evaluated the possible resonance between building and soil?
I have difficulties to hear you. You ask if we have investigated the correlation between buildings and...
Sorry, Marco, can you repeat your question because we cannot hear you properly?
Have you evaluated the possible resonance between a building and the soil?
Oh, okay. Not really, not at this stage. We have assumed a value for the vulnerability of the buildings, considering the main height of the buildings and approximated shape period between 0.2 and 0.3 seconds. What we wanted to investigate at the moment was just the spatial distribution between the damage degree and the results of the microzonation to better understand this specific spatial distribution. But we would like to go on with these studies. So any contribution or support is really welcome.
Okay.
Okay. Thank you, Marco. Thank you again, Sergio, for your presentation. So I'm going to introduce you the last presentation of our workshop and of this morning session. Of course, I do apologize because the presenter is Salvatore Scudero and not Antonino D'Alessandro. So please, please, Salvatore, excuse me for such misunderstanding. Salvatore Scudero from INGV, the Italian National Institute for Geophysics and Volcanology. Optimization of low-cost monitoring systems for on-site earthquake early warning of critical infrastructures. And in this work, the authors, Antonino D'Alessandro, Salvatore Scudero, Giovanni Vitale, Andrea Di Benedetto, and Josuelo Bosco, introduced the optimization of an already established seismic and structural monitor system in order to make it suitable for the implementation in case of earthquake early warning. So I leave the floor to Salvatore for his presentation, and you're welcome.
Hello, everybody.
Good morning, Salvatore. You can share your screen by clicking on the icon in the lower. Okay.
Can you hear me?
Yes, perfectly.
Okay, so I start. Hello, everybody. So Maurizio recalled the title.
Cliente dalla nota in direzione di Ancona, 60 minuti il tempo di percorrenza.
Okay, it's the optimization of an already existing monitoring system that we built in the last couple of years. So this is the system, and it's based on micro electromechanical sensors and has been used for earthquake observation, structural health monitoring, and post-earthquake disaster assessment. This is the setup of this system. It's based on a single board computer. It's a Raspberry Pi, and the MEMS sensor is a triaxial accelerometer with a gyroscope. Here in the tables, there are the details of this system. The system has been deployed since 2018 in some cities in eastern Sicily that we know is a really seismic risk prone region in Italy. And we had nice results. We've been able to record earthquakes, even small 2-point-some earthquakes, and to study the building behavior as it responds to such small events. And such small network are been developing to time. We start with few stations there, and we are expanding the number of nodes in each network and also the number of networks. One of the characteristics of such urban scale or even building scale network is the possibility to implement a system for early warning in case of strong earthquake. As you know, probably there are two different approaches for earthquake early warning system. First one, which is based on a network, it's used in the case that the source region of the earthquake is far from the target region for to send the alarm. So usually there is a warning time of even some minutes. Differently, when the target area is very close to the source region of the earthquake, another approach is based on the single station. So it's the same station hosted in the building that send the alarm for that building. In this case, the time for the alarm is really short. So the optimum of this system is for target region not far more than 50 kilometers from the source region. In this case, we have just 20 seconds of lead time, but usually much less. So in this view, the system we build up is in the hosted in Eastern Sicily, so where the source of the earthquake are really close. The single station, the on-site early warning system is the method, the approach we adopt. And in this case, where the time is so short, we need to be fast to compute the data. So first of all, we converted the code from Python to C, and we had a great improvement of the performance of the seismic station. And then, it's the main part of this work, we coded a trigger algorithm. So a system that can automatically detect the upcoming of a seismic wave. It's a novel approach. It's quite simple and quite easy to implement. It's based on the standard deviation calculated for moving windows with variable duration, and each value calculated for the windows is normalized to the previous window. So we deal with relative energy variation rather with absolute variation. And we set up also 10 different trigger levels simultaneously, so that we can deal with different type of earthquakes with different frequency content. We tested the system with simulated earthquakes with a magnitude 3 event at 50 kilometer distance. On the top left, there is the signal. Top right, the value of SD calculated. But what most important is in the bottom right is the trigger time for this type of event, a magnitude 3. I showed some later. We did the same for a magnitude 5 earthquakes at same distance. The frequency content is obviously different, and we compare now the result. The black line is the time we calculated for each combination of window and level of threshold, and the blue line is the reference line, so the theoretical time at which the first wave arrived. In all the cases, we've been able to get the first seismic shaking in few tenths of seconds. And it's quite robust result, even though we need to validate the system through dedicated, more detailed statistical analysis to define standard tests to assess the real performance of this algorithm. And the next step will be to tune the system for some representative application within the wide range of potential real cases. Just starting from the network we build up since 2018. So thanks for your attention.
Thank you very much, Salvatore, for your presentation. Very interesting. And I would ask if the other participants have any question for Salvatore about his work. No questions. So just a question about the sensor, the MEMS sensors. For an operational application of such a kind of monitoring system, early warning systems, how much sensors should be deployed, and which are the average costs of such a kind of installations, if compared, for example, with traditional monitoring systems? Have you...
The cost for each of this system is a couple hundred euros, 250 euros, so it's quarter of 100 less than the traditional sensor. Theoretically, one of these sensors is enough to send an alarm. Of course, it would be easy to get a fast alarm. So a feedback from a small network it's preferable rather than a single one. So I think for a building, 2 or 3 sensors could be enough, and for a town like Catania is a big town of 500,000 people. I guess 10 monitoring stations, maybe less, 7, 8 would be enough to have a robust alarm, avoiding false alarm.
Okay, thank you for your clarification.
You're welcome.
Salvatore, please, you can stop your sharing.
Yes.
So that. Thank you again. So we can move to the conclusion of our workshop. So I would ask to Marco if he would provide this conclusion to these 2 sessions.
No, it's good. It's good.
Okay. So I think
under your coordination.
Yeah, I think that it was an interesting session in which we have the possibility to. Sorry, there is some microphone switched on, and I. Okay, it's okay now. I say that it was a very interesting session, and for this reason, I would like to thank you to the authors for their works, for their presentation, and we collected 6 6 papers for our workshop. It was an important result. Our workshop was issued the first time in 2017 in Trieste. So from that first edition, we have several occasions to discuss during the ICCSA conference. This is the first time that we are going online. It is also another way to share our experiences, our projects, our research and advances. But I hope that the next year we will able to return to a normal situation with a live conference in the real sense of the word. So the next step is ICCSA 2021 and the next edition of Aster Workshop 2021. And then thank you to all very much. Thank you to Marco, to Chiara, and Amedeo as co-organizers of this workshop. And thank you to the authors and to the other co-authors that have presented their works. See you again in ICCSA 2021.
Thank you for his kind and very good management of the session. Thank you very much.
Just a reminder for the chairman to fill in the evaluation form about all the speakers of today.
Okay, and thank you, of course, thank you, Angela, for your support during this session.
You're welcome.
Okay, goodbye, everybody.
Thank you, everyone. Goodbye.
Have a good day.
Goodbye.
Bye. Bye.
Bye-bye.